Welcome to Renaissance Timing University. I'm Adam Wertheimer, an application engineer at Renaissance, and today I'm going to be talking about the difference between a clock synthesizer and a jitter attenuator, using our VersaClock 7 product as an example. The end of the video will be a demo of the synthesizer mode on this product using one of our eval boards and phase noise analyzer. So a synthesizer part has a couple different components. It has the X-in block, which takes the crystal and makes a reference frequency. That frequency is taken to an APLL to multiply it up to a high frequency. Then you have a divider to divide it down to the frequency you need for the output. In this part, we have two different dividers. We have an IOD, an integer output divider, and an FOD, a fractional output divider, to go from the high APLL frequency, which is typically around 10 gig for this product, to your output frequencies. The IOD is an integer output divider, so it can divide by 1 over n, while the FOD is a fractional output divider. It can divide by an arbitrary m over n. The advantage with the IOD is better jitter, that you'll always have a cleaner signal with a 1 over n divider, lower phase noise. The advantage of the FOD is that you can generate an arbitrary signal via any ratio. So looking at that from a synthesizer, you can add additional blocks to make it a jitter attenuator. And a jitter attenuator has the X-in and APLL, which I showed on the synthesizer, plus a DPLL block. So what you can do with these two blocks together is you can use the DPLL to follow a clock-in signal for frequency and still get the jitter of the APLL on your outputs. So the DPLL and APLL both have bandwidths associated with them. The APLL bandwidth is typically in the 400 to 500 kilohertz range, while the DPLL could be from about 0.1 to 100 hertz. Typically, it would be 25 hertz for a standard JA, but you have some leeway on what you can use. So with the APLL and DPLL, the DPLL is used to steer the APLL frequency to match the fractional frequency offset of your clock-ins through the filters that I was just describing. Again, a jitter attenuator can go to an FOD or IOD, but I'm introducing another concept here called a bank, where you have a single divider, an FOD or an IOD, going to multiple outputs. These outputs will have to be at the same frequency, but typically you'll have a number of clocks at the same frequency, whether it's 100 megs or 156.25, depending on the application. One other feature of the VersaClock 7 that I want to mention is the bypass path. So you can go directly from X-in to certain outputs, and you can go directly from clock-in to certain outputs. So these two give you the flexibility to add these extra signals that bypass the APLL and DPLL for certain designs. The VersaClock 7 has two different sets of variants. The RC210, which is a synthesizer only, like this, and the RC310, which is synthesizer or jitter attenuator, which looks like this. Finally, I want to show an example of the RC21005, but BQ, with the Q variant, meaning it has an internal crystal, and that's what I'm showing here. So using the internal crystal and the synthesizer mode, I'm multiplying up to a high frequency and dividing down to 156.25. And in this case, you can see I get a jitter of about 150 femtoseconds. And this is done without an external crystal on the board or other crystal load components, which helps the BOM. So it might be useful for certain designs. So thank you for watching this video. Please look for other videos from Renaissance Timing University.